Good day, ladies and gents. Welcome to this next worked example. Today we're going to be looking at connection dyes, specifically bolts, and looking at a bolt group, the eccentric loads in the plane of a bolt group designed to SANS 10162 Part 1, the South African Code of Steel Design, and this is part of the Stellenbosch University Design course, Structural Design 424. Now, here's our example. Connection design, bolted connection. Consider the connection shown below. A force of CUX equals 20 kilonewtons and CUY equals 200 kilonewtons applied. All the plates for the connection are 20 millimeters thick. Determine a suitable bolt size. So here we have a connection carrying two loads, a vertical load and a horizontal load applied to the end of this connection, and this is bolted each side of a column. Now these could be probably a crane load or something like that, especially when a crane starts or stops. You can have a lateral load, and then you've got the vertical load from the payload that the overhead gantry crane is carrying. And so what we need to do is start determining the bolt size of these all on the side and making sure that they are sufficient. So we're going to go through the methodology of how to do that. So we're going to go look at the calcs and see how to determine this. Make sure you get hold of a set of these notes, or alternatively you can just write them out, and we'll start going through them now. Firstly, we need to make sure we understand what is happening in this problem. Now, firstly, determination of bolt size. We need to know what sort of load. And just going to make a note there. The load will be carried by shear in bolts, because it's going to try shear through the bolts each side. And just be careful, there are two sets of bolts, one each side of the column. But now also the eccentricities of each force relative to the center of rotation cause moments about the center of rotation. We're going to have a look at the center of rotation now, because that's an important position to consider. Center of rotation. Now, looking at the forces in this connection, there is our connection, looking down at it, and we need to convert the forces we've got to something acting at the center here. In the same way we design beams and columns and such about their centroid, we are designing this about the center of rotation which exists there. Because what we need to do, we have the two forces applied here, coming back to our example, two forces there and there. I'm going to convert the vertical force and the lateral force to be a vertical force, lateral force, and moment about the center of rotation. And then from that, determine the forces in all the bolts, work out which is the most stressed bolt, and then design the most stressed bolt, knowing that all the others will inherently satisfy the requirements and regulations. So, having a look at this coming back, what I'm going to do is first shift those forces, as I mentioned to you first. So now, if I have a look at this center of rotation, I'm just going to draw it at the side to make sure that there's space, because I'm going to put a whole bunch of arrows on the diagram just right now. So at center of rotation, I'm going to draw the forces acting there. I'm going to put the vertical force downwards, so we've got this force CUY, and I'm just going to call it CY prime, just to remember that this is not the total force, this is only half the load. And then I've also got a horizontal force, which is smaller, CUX primed, and then I've got a moment acting about this position, due to these eccentricities, because they're acting not at the center of rotation, and I'm going to call that MU primed. Now let's have a look at what forces those will apply. So that is just that position there, those pointers there. I've just moved it across so you can see it clearly. Now, we've got to distribute those forces to the different bolts, and the vertical forces and horizontal forces are relatively straightforward. We simply take the vertical force and divide it by the number of bolts, and this will give us a vertical component in each bolt. So roughly CUY over 6 will be carried by each bolt in the group. So that's what we've got. I'm just drawing the vertical component in each bolt. And then once again, the CUX, the horizontal component, will be carried by each bolt. So that is distributed around all of those bolts. The next what we need to do is consider the moment, because the moment is now about this center of rotation, that moment there, and from first principles, moment is always force times perpendicular distance. So we've got to look at what axis these forces are acting about and what line they're perpendicular to. So I'm going to draw a line from each bolt through the center of rotation. So this will now be perpendicular, this line I'm drawing, to the forces acting. So that's what I've got. And so if I look at this top right bolt, I'll have a perpendicular force acting there. The middle one, I'll have a vertical force at the position of the bolt. Bottom right, something acting down. The magnitude of the 4 outer bolts will be the same, and the magnitude of the inner ones will be the same. These ones are smaller because they're closer to the center of rotation. So those, we now have components in all the different directions due to all these forces. And if by looking at those forces, we can start quickly identifying which bolt is the most heavily loaded. Because by taking the vector sum, we'll see this top right bolt here has all the forces acting in the same direction. So we're going to end up a resultant in this general direction here, whereas this one is similar, although the horizontal components of the green and blue line cancel each other out, and then alternatively these ones, the upward and downward, cancelling each other out. So our top right bolt is the most stressed. And just to confirm that, I've just drawn this again, just a little bit larger so you can see exactly what's happening. Here is our bolt group. That's the forces applied at the center of rotation on the right. And there's our center of rotation, so all those forces acting about there. This diagram here represents what happens to the bolt's forces as it gets further. Same as plane sections remain plane and stress is proportional to distance from the neutral axis. It's the same for a bolt. So if I have a bolt at that distance on the center line, so this line here I've drawn in green would be this middle line. At half the distance, half the load. Full distance, full load. So as we get further, the bolt force increases, both horizontally and vertically. But also what you should consider quite carefully is the y distance. The distance vertically affects the horizontal force, and the distance horizontally affects the vertical force. So what we will see shortly is that we need components and distances from the center of rotation when working out the force in the most stressed bolt, because we need the information for that bolt. And for that specific location, our y dimension is quite important. So that's our y, and it's just bolt number J, and then also our x distance of it. So you'll see here the force vertically, the y component in this outer bolt is proportional to its x component, and the horizontal component of force is proportional to its y distance. And you'll see those starting to appear in the equation. Now, in this example, I'm going to put everything from first principle. So there are simpler single-step equations that can be used for solving this. You'll see them in the green book, but I'm going to go through each, but step by step. So there is our most stressed bolt. Now let's start having a look at this. And just to make a note, the most stressed bolt, most heavily stressed bolt is the top right. And this is due to what we have just shown in this example, that because of the vector sum. Now we're going to start calculating the capacity and checking what the forces are. So firstly, forces in the bolt group. I'm now going to just calculate what are the forces in the bolt group. So this is what I was talking to you about earlier. And firstly, I need to consider it a load per side. And this is where I wrote it as CUX prime, simply that it is the total load in the x direction divided by 2, and that gives me 10 kilonewtons horizontally per side. And then my y component is the exact same thing. It's CUY over 2, and this is 100 kilonewtons horizontally. And then the same, we need now a moment about the center of rotation. I'm just calling per side. This is to do with the horizontal component at its vertical offset plus the vertical force times its horizontal offset. So we must make sure of that, so that when we are looking at this, I've got a CUY value which is acting at 200 plus 50, and then a CUX acting at 175. So from the center of rotation to the force. So that's where I'm getting the values we are now dealing with in the calculations. So this is going to be 10 times the 175 plus the 100 times the 250 millimeter distance, and that gives me a moment of 26.75 kilonewton meters. So that's the force acting about the center of rotation of the bolt group. Now what I'm going to consider is the force per bolt. And once again, as I explained here, I am breaking this down and calculating it in 4 separate steps, where there are equations where you can do this in one step. I just want to do this for clarity, so you can see where all the numbers come from. So this is now the force per bolt. Forces in most heavily loaded bolt is the horizontal component divided by the number of bolts, 1.667. I'm not putting in all the numbers, you can go do that afterwards. I'm just doing that so we don't spend too long writing everything down. And once again, the vertical component is the same. It's uniformly spread amongst the bolts. So we've got 1.67 kilonewtons horizontally and 16.67 kilonewtons vertically. And I just want to note now, the moment will cause both horizontal and vertical force components in the bolt. In the bolts considered. And we're going to call those the vertical component FMUX primed and FMUY primed. That's just to explain that once again. We've got a force, a diagonal force here. I'm going to convert it into a horizontal component and a vertical component. And just so you can also see once again where this is all coming from. Now, moving along with the equations, I'm going to now calculate those forces I mentioned, which is FMUX equals YI and then also our y component is proportional to the x distance, as I mentioned earlier. And this is linked to the polar moment of area, IP. The polar moment of area quantifies the stiffness and the influence of where the bolts are. Because as the bolts get further away from the center of rotation, the force that they can take it has a they have a greater influence. They are much stronger because the maximum force per bolt remains the same per size, but as it gets further, the lever arm increases, so that is beneficial for us. So we're going to now quantify the positioning of all the bolts with the polar moment of area, where IP is the polar moment of area. And this is given by, is the sum of from I equals 1 to n, so this is of all the bolts, from xi squared plus yi squared. And this should look familiar. That is just a distance. X squared plus y squared equals L squared, the distance. So if you know what the perpendicular distance is, you can just use that. Otherwise, if you've got x and y components, which is more commonly the case, we're just going to use those. So in terms of, we've got 4 bolts with 100 millimeter distances, plus 4 at 50. And these are the top and bottom bolts. So those are the x and y components of those. Plus, our middle bolts, we've got 2 with a 0 millimeter y component and a 50 millimeter x component. So those are just the middle bolts. So top and bottom bolts, middle bolts, 4 at 100 millimeter vertically, 4 at 50, and then another 2 at 50. So that gives us the polar moment of area, quantifying the positioning of all the bolts, 55,000 millimeters squared, and it's in units of millimeters squared. And so once we've got that, we can now compute what is the force per bolt. So this is the force due to moment horizontally, due to that moment. And I'm just filling in the values in the equations we wrote above, and then working out what the horizontal and vertical components are. And then that means we've got a 48.64 kilonewton force horizontally due to the moment. And we're going to find a similar sort of problem with the vertical component. Times 10 to the negative 3, that's just to convert it from newtons to kilonewtons. And so there we go. We've got 48.64 kilonewtons horizontally, 24.32 vertically. And once again, the vertical component affects the horizontal force, and the horizontal distance affects the vertical force. And if we now start graphing this and just doing a vector sum of exactly what's happening, we're going to end up with a diagram that looks like this, where here is our force horizontally due to moment. Here is our force vertically due to moment. Here is our force horizontally due to the axial or the longitudinal shear force. And then here is our force due to CUY. So vertical components, horizontal components, and we're actually interested in this. We're interested in the maximum force. So this, I'm just going to call the ultimate force in the bolt. That's what we ultimately want. If we know that, then we can check that the force is correct and sufficiently design it. So our force in the bolt equals the vertical components plus the horizontal components. So add the so those are my horizontal components, and using Pythagoras I'm going to add on just the other components vertically, and so there is our final equation, and that gives us a force of 64.9 kilonewtons. So we've got 65 kilonewtons, roughly 6.5 cars, hanging from this bolt in shear. And we now need to make sure that that bolt is sufficient for this final resultant force that is applied to our bolt group. So now we're going to go into the bolt design and the bolt calculations. We're going to using grade 8.8 bolts. And assuming our diameter is greater than 16, because you will see in the guidelines different ultimate stresses between whether it's 16 below or 20 mils and above. Therefore, our ultimate stress in the bolts is 830 MPa. And assume threads in failure plane. Because you'll see in the calculations and guidelines that you can either assume that the bolts are in the failure plane, or the threads are in the failure plane, or the threads are not. Now, it's normally conservative just to assume that where the bolt will shear through, that's where the threads are, because we actually might not be sure on site. So now we're going to check the shear resistance and make sure that is sufficient. So we've got our shear resistance is equal to 0.42 times our partial factor area of bolt ultimate stress, and this must be greater than the force per bolt. And by using the area of bolt is pi over 4d squared, and phi b is 0.8. Now just be careful with this phi b factor. You'll see in different places it has different values, so just be very careful you do use the correct value depending on what you are designing. And if we solve all of this, I'm not going to go through all of that, solving, we get our diameter of bolt must be greater than or equal to 17.2 millimeters. So now we can use a M20. Therefore use M20 grade 8.8 bolt. Now that we've got a diameter, we can check the rest of the specifications. We also now need to look at bearing resistance on our section and then go through that to get our results. So just moving on to the next page, we're going to now check bearing resistance. This is the equation now for bearing resistance. 3 phi BR. And this must be greater than the T thickness. We need to be quite careful about that, because in our setup we have this bolt is bearing both against the 20 millimeter plate of the connection and the 11 millimeter thick plate of the column flange. So as it does that, we need to make sure that the weaker one is checked. So obviously in this case, the column flange is thinner than the connection plate. So we're going to check T as the thickness of the flange. Now, just be careful though, in each side the forces are applied in different direction, whereas now on the plate there's going to be bearing, where on the column, the bottom there is going to be bearing. So it just bears on opposite sides when you're doing the calcs. But now, as I was mentioning, T equals 11 millimeters, since column flange thinner than the connection. So we're going to use that value. And then also we need to make sure we're using the ultimate stress of the steel. Just be careful, I've written FU and I've just added an S on the end just to remind you that this is not the same as the bolt capacity used above. This is 470 MPa of steel. And it's quite easy to make that mistake to plug the bolt capacity when you're checking bearing, and bearing is a steel failure problem where the bolt pushes and squashes the steel next to it. Now we're solving this. You'll find that D is greater than or equal to 6.2 millimeters. So therefore an M20 bolt is okay. Now once again we also need to check bearing resistance at the edge distance. The problem we have in this case is that the edge distance is not well defined because we have a resultant at some angle between all of these coming down. So from the middle of the bolt to where the bolt would pull out is a diagonal, which we haven't calculated. But this doesn't often govern depending on where the bolt is, but we should always check it. And all I'm going to do is I'm going to find out what does the distance need to be, because if I have a look at this distance from the bolt to the end is 52 millimeters, and so a diagonal will be a lot more than 52 millimeters. So as long as I know that I need a bolt distance less than 52 mils, my calculation is fine. I don't need to go to a more detailed calc. So here once again my bearing resistance is 5BR AT N of the steel, and this must be greater than the force per bolt. Now, solving this, we'll find that A must be greater than or equal to 18.7 mils. So that's the distance from the middle of the bolt to the edge where it pulls out. Thus, we're okay, because edge distance is greater than 52 mils. As I mentioned, therefore, okay. We don't need to worry about that further. It's far in excess of what we need, so we're not going to worry and do a detailed calc. Thus, in conclusion, grade 8.8 M20 bolt sufficient. And we have solved the problem then. Okay, so just a reminder of what we did. We took our connection, we converted any force and every force that acts on it to the center of rotation per side. We had two sides, so we halved the total forces, applied them each side. Then we had to look at the components, and we applied those forces to each bolt, and then from that I could identify which bolt we needed. And then from that we know what the X component and the Y component, the distances are, the XI and the YI distance. Then we could work out all the different components to that. From that we got a resultant force, and then checked that the resultant force could be carried by a bolt, and we found that that was sufficient, that a 20 mil bolt could carry. As I mentioned previously, this was a very detailed step-by-step showing all the different forces. However, in a test or exam for this course, there is nothing wrong with using the equation in the green book, provided it's used correctly, and then you can do it in one step. But this is just to explain where all those numbers come from. Thank you very much.